Welcome everyone. The class will be on the concept of adjoints and inverse of a matrix. First, let us try to understand what is minors and cofactors. The minor of an element of a determinant of order n is a determinant of order n minus 1. That means if you want to find a minor of an element of a determinant, you get another determinant. The order is decreased by 1. That means if the initial order is n, then order of the determinant is n minus 1. Next, what is cofactor? Cofactor of an element aij. Say this is an arbitrary element aij is defined by, this is a symbol for cofactor, capital Aij is equal to minus 1 to the power I plus j. That is I and j to the power I plus j multiplied by mij. What mij stand for? Mij is nothing but the minor of the element of the position ij. Okay, so let us try to understand these two concepts, minor and cofactor, with the help of simple example. Okay, find the minors and cofactor of the element of, say, the determinant. Say, first we are going to find the minor of 5. What I say in the definition, that minor of any element in a determinant is another determinant, but the order obviously will be reduced by 1. So if we take the minor of 5, then you will get a determinant where you need to ignore this particular row and you need to ignore this particular column. So what will be the order left? Order left is 2. That means we are going to get a determinant of order 2. And what is the determinant? 0, 1, 2, 3. So 0, 1, 2, 3. And since the position of 5 is 1, 1, therefore the minor of 5 is denoted by m1, 1. And you can calculate this, since you can evaluate this determinant. So if we calculate this, what will be the value of this minor? So if we calculate the value, so it will be 3 into 0 is 0, minus 2 into 1 is 2. So this is equal to minus 2. That means the minor of 5 is minus 2. Similarly, let us try to understand minor of some other elements. Say minor of 8. Minor of 8. In case you want to calculate the minor of 8, what I'm going to do is, you will ignore this particular column and you will ignore this row. Then what elements will be left out? We will left out with 2, 0, 1, 2. 2, 0, 1, 2. What is the position of 8? The position of 8 is 1, 3. Therefore, the symbol for minor 8 is M13. M is the symbol for minor and A, capital A, is the symbol for cofactor. Both are very simple concept, but we need to understand what is the basic difference between minor and cofactor. So let us try to understand what is the cofactor of 8. The cofactor of 8 is equal to minus. To find cofactors, it's minor to be multiplied by a term minus 1 to the power I plus j. Now, in case you want to find the cofactor of 8, what is the position of 8? The position of 8 is 1, 3. Therefore, the suffix is 1, 3. So, minus 1 to the power 1 plus 3. So, M13. Let us calculate what is M13. So, you can calculate M13. So, we evaluate this 2 by 2 determinant. 2 into 2 is 4. Minus 1 into 0 is 0 is equal to 4. So minor of 8 is 4. Now let us calculate the cofactor of 8. Now this is minus 1 to the power 1 plus 3. Minus 1 to the power 1 plus 3 is equal to minus 1 to the power 4. Minus 1 to the power 4. So what is M13? Already you have calculated M13. M13 is 4. So M13 is 4. So minus 1 to the power 4 is equal to plus. So therefore this is equal to 4. So what we have seen, let us compare. Minor of 8 is 4 and my cofactor of 8 is also 4. So to calculate the cofactor of 8 and minor of 8, there is no difference. So how to decide where there will be a difference in calculation of minor or the cofactor? It depends. Then what is the position of this element, the position of this element is 1, 3. So 1 plus 3 is an even number. In case the sum of the suffix is an even number, so there won't be any difference between the value of the minor and value of the cofactor. In case if we take any other element, let us calculate one different element. Okay, so here we'll take the example of 3. So we want to calculate the minor and cofactor of 3. So what will be the minor of 3? We'll calculate m1. This is the position, 1, 2 positions, m1, 2. M1, 2. That means we are going to calculate the minor of 3. So in case you want to calculate the minor of 3, you have to ignore this column. You need to ignore this row. So what will be left out? 2, 1, 1, 3. 2, 1, 2, 1. This is 2, 1, 1, 3. 1, 3. So now you calculate 3 to the 6 minus 1. So it's equal to 5. So this is the minor of the element 3. Let us calculate the cofactor of the same element. Okay. The cofactor of the same element is A. Cofactor is denoted by A, and the position of the element is 1, 2. So 1, 2. So this, to find cofactor, always you need to multiply the minor by a term minus 1 to the power the sum of the suffix. Sum of the suffix means 2 plus 1 is 3. Then m1, 2. This term to be multiplied by the minor of the same position element. So what is minus 1 to the power 3 is minus. Then m12 already you have calculated is 5. So it will be minus 5. So what you have said? That for element 3, the value of minor is 5. The value of cofactor is minus 5. So for those elements where the sum of the suffix is an odd number, then the value of the minor and the cofactor will be differed by a sign. Let us move ahead. Now let us try to understand what is the adjoint of a matrix. Let us calculate the adjoints of this matrix A. So this is a general matrix A11, A12, A13, like that. A31, A32, A33. So what is adjoints of a matrix? To find adjoints of a matrix, what you need to do is first you need to find the cofactor of all these elements. How many elements are here in this matrix? 9 elements are there. So you need to calculate the cofactor of each and every element. We are calculating that. So this is A11 stands for the cofactor of small a11. As I said before, that capital A stands for the cofactor. So the moment you write capital A11, 12, you should understand we are writing all these cofactors. We are writing the cofactors, respective cofactors. Okay, the cofactor of A11, capital A11, cofactor of small a2 is capital A2. Similarly, the cofactor of A33 is capital A33. So we are writing the cofactor as it is. But writing the cofactor as it is, you don't get the adjoints of a matrix. What you need to do, extra one important steps to be done. What is that? This element, you have to write the transpose. You have to take the transpose of this matrix. The moment you take the transpose of this matrix, this first row will be the first column. That means you interchange the rows and columns. The moment you interchange the rows and columns, then finally you get this matrix. And this is said to be the adjoints of the matrix A. So to find adjoints, you need to find the cofactor each and every element. Let's move ahead. So we have a shortcut method to find the adjoints of a matrix ordered 2 by 2. Let us see how to find out. Let us take a matrix. Say we'll take this matrix as A11, A12, A21, A22. Okay, in that case, to find adjoints of a matrix, shortcut method is this. That you need to, this is a diagonal element, A11, A22. So you need to interchange the diagonal element. This A22 you bring here, and this A11 you bring here. And these non-diagonal elements, this is A12, this is A21. These non-diagonal elements you write as it is, but you change the sign. Say initially our matrix is A11, A12, A21, A22. So to get the adjoints by a shortcut method, you interchange these two elements of the diagonal, like A22. In place of A11, you shift this A22, these positions, and A11 you bring these positions. And don't change these two elements. This element you need to write as it is. Okay, say A12 will be A12 only in the positions, A21 will also be in the same positions. But if it is a plus, you have to make it minus. Then there will be changes of sign of the elements which are in non-diagonal positions. Okay, let's see the next concept. Here we are going to discuss another very important concept, how to find the value of a determinant with the help of cofactors. Okay, so what is the question? Using cofactor of second row, cofactor of the second row, that means we can find how many elements are there? Here 9 elements are there, we can find 9 cofactors. But the question is, using cofactor of the second row, you need to only find cofactor of this 2, 0, 1. You need to find the cofactor, evaluate the determinant. That means to find the value of a determinant, you don't need to calculate the cofactor of all the 9 elements. Okay, why? We are going to discuss this point. First, we'll calculate the cofactor of this second row. Second row cofactor you can calculate like this. First, what is the position of this? This is 2, 1 position. So we'll find A21. So the moment I write A21, it means we know that we are going to find the cofactor of this 2. Then next I'll write this is 2, 2. That means I am going to find the cofactor of 0. Then I need to find A23. That means I am going to find the cofactor of 1. Now A21, the moment I find the cofactor of this position is 2, so I need to write minus 1 to the power 2 plus 1, that is 3. Okay. Then if you find the cofactor of this element, so you need to ignore this row and this column. What will be left out? There will be a determinant of less order. The determinant it is 3, and if we find the cofactor of an element, the determinant will be reduced to 2 by 2. So you need to multiply 3 into 3. That is 9 minus 3 into 3, then 8 into 2. That is minus 16. So this is minus 1 to the power 3 is minus. Then 9 minus 16 is minus 7 is equal to 7. You got this. A21 is 7. Now we are going to calculate A22. A22. So A22 is minus 1 to the power, sum the suffix 2 plus 2. It's 4. Now we want to find the cofactor of this element. You need to ignore this column, this column and this row. This column and this row. What elements will be left out? 5, 8, 1, 3. We need to multiply 5 into 3. 5 into 3 is 15 minus 8. So you need to multiply 15 minus 8. 15 minus 8 is 7 and minus 1 into 4 is plus. So it will be only plus 7. Now finally A23. A23. That means we need to find the cofactor of this 1. So you have to find the cofactor of 1, you need to ignore this row, you need to ignore this column. Okay, what will be left out? We will be left out with 5, 3, 1, 2. 5, 3, 1, 2. So let's multiply this. 5, 3, 1, 2. This is minus 1 to the power, minus 1 to the power 2 plus 3. This will be obviously 5. Okay, you have calculated a cofactor of 1, so you need to multiply 5 into 2. This is 10 minus 1 into 3. This will be 3. This is equal to minus 1 to the power 5. Minus 1 to the power 5 is minus 10 minus 3 is 7. Okay, finally you are getting minus 7. So you got the cofactor of the 3 elements 2, 0 and 1. So now let us calculate the value of this determinant. If the value of the determinant is denoted by delta, then the value is obtained with the help of, first I will write the element. This is A21. Then that element I will be multiplying by the cofactor of the same element A21 plus, next I will be writing this element, that is A22 element. Then I will multiply that element with the respective cofactor. Respective cofactor is A22 plus, this element will be what? This element will be A23 and this is multiplied by A23. So what I have done is, the value of the determinant, to calculate the value of the determinant, as it is asked to calculate the value of the determinant along the second row, I am writing the second row element and each element I am multiplying by the respective cofactors. First I have taken this element 2, then 2 I have multiplied, that is a21. 2 means the position of a21, 2 is a21, that a21 I am multiplying by respective cofactor, a21. Then next 0, that is a22 is 0 element. Then what is the cofactor of this position element? a22. Next is 1, that is a23 position, then multiplied by the respective cofactor, that is capital A23. Let us calculate what will be the value of this particular determinant. So, yes, a21, what is a21? This is 2. Multiplied by the cofactor a21, a21 is 7, right? Then plus a22, a22 is 0, so we don't need to multiply. This 0 multiplied by a22 element obviously will be 0. Next a23, what is a23? a23 is 1, and 1 is multiplied by the cofactor of that element a23. a23 is minus 7. Minus 7. So finally 7 to the 14 and minus 7. So your answer is 7. That means the value of this determinant is 7. So now one simple question here, that can you evaluate this determinant with the help of the other rows or other column or not? Yes, obviously we can calculate the value of this determinant with respect to the other row or the other column. But what happens if we take the first row? Say we are taking, for example, if we take, I'll show you this. First what I'll take the first row. Let me write the first row element. Say first row element A11. Then what I'm going to do is, each element I'll be multiplying the cofactor of some other row. Say first I'll be writing A11, then I'll write the cofactor of the second row, A21. Then I'll take the second element of the first row, A12. Then I'll take the cofactor of this element. So this is A22. Then finally I'll take the element A8, that is A13. Then I'll take the cofactor of other row, that means the second row, that is A23. So what I have done, I have taken the 3 elements of the first row, then each element I am multiplying the corresponding cofactor of the second row. Then the value of this determinant will always be equal to 0. That is a very important point. Okay, so value of a determinant can always be obtained with the help of a particular row and multiplied by the respective cofactors, and after multiplying each element by the respective cofactor we need to add, then we'll get the value of the determinant. Next, we are now going to start a very important theorem. What is the theorem? The theorem says, if A be any given square matrix of order n, then A multiplied by adjoints of A equal to adjoints of A into A equal to determinant of A into I. This is identity matrix. I repeat the theorem. If A be any given square matrix of order n, then A into adjoints of A is equal to adjoints of A into A is equal to determinant A into I. How we will just verify this. Our verification is very simple. First we'll take this left hand side, we'll take as A adjoints of A. We'll consider a 3 by 3 matrix A11, A12, A13, A21, A22, A23. Done? Next, A31, A32, A33. Then we'll multiply by adjoints of A. What is adjoints of A? That is A11. To find adjoints of A, we have explained in the beginning of today's class that first you need to find the cofactor of all the 9 elements, and then you need to take the transpose. So first cofactor of A11 is A11, then cofactor of A12 is capital A12, but you need to take a transpose. Therefore cofactor of this first row I will write as a column. So A11, A12, then A12, 1, 3. Then find the cofactor of the second row. So A21, then A22, then A23, A23. Find cofactor of each row and write as a column. Because you are finding all 9 cofactors, then you need to take the transpose. So finally, A31, A31, A32, then A33. So you need to multiply this. Observe these multiplications very carefully. How do you multiply this? Okay. So if you multiply this, look, how do you multiply? First, when you multiply this is A11, then you will multiply by capital A11. That is A11 multiplied by capital A11. The next A12 multiplied by A12 plus A12 capital A12. Right? Then what will be left out? A13, A13 plus A13, A13. It means I am multiplying this row with this column. So A11, A11 plus A12, A12 plus A13 into A13. Okay, so I can just repeat these steps here. A11, 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 A11 plus A12, A12, then A13 plus A13, A1, A13, A13. Okay, then what I'm going to do? Then I'm going to multiply this one with this. What is this? This is first row and this was the cofactor of. Can you tell me what is this? This is the cofactor A21, A22, A23. This is 6, A21, A22, A23. This is the second row and these are the cofactors. You are multiplying the first row with the cofactor of the second row element. So obviously if you multiply this with this, the second element has to be 0. Here the second element has to be 0. Next, you are multiplying the first row with the third row cofactors. The first row with the third row cofactor. So obviously this will also be 0. Now let's move ahead. First, we'll continue with the second row. The second row first, we'll multiply the second row with the first column. What is this first column? This is A11, A12, A13. These are the cofactor of the first row. And this is the second row. If you multiply the second row with the first row cofactors, then obviously it will be 0. So this element will be 0. Now coming to the A22 position element. So to get this A22 position element, second row to be multiplied by this cofactors. A21, observe these numbers, A21, A21, A22 plus A22, A22 plus A23, A23. So I am going to get this element. So we are getting A21, A21, then A21 plus A22, A22, then A22, then plus A23, A23. That means you are multiplying this element with this row cofactors. This is the second row and these are the corresponding cofactor of the second row. So next, third element. This is first, second, third, fourth, fifth, sixth element. To get the sixth element, you need to use the second row and the third column. Now second row, what is this? A31, A32, A33. Capital A31, capital A32, capital A33. These are the cofactor of the third. These are the cofactor of the third row. A31, A32, A33. So these are, you compare the suffix, that is 31, 31, 32, 32, 33, 33. So these are the cofactor of the third row. But you are multiplying the third row cofactors with the help of the second row. So obviously it will be 0. So similarly, if you continue this process, third row, if you multiply to get this element, this is the third row, first row cofactor 0. Then this is the third row, second row cofactor 0. Then how to get the last element, 3 elements. So it will be A31, 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 A31 plus A32, 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 A32 plus A33, A33. Okay. Now let us see this element. What is this element? A11, capital A11. A1. I'll just write this element here. A11, capital A11 plus A12. This is A12. This is A12. A13, A13. It means first row and corresponding cofactor of the first row. So just now we have explained that if you take a row and if you multiply each and every element by the corresponding cofactor, you get the value of the determinant. So this is nothing but is equal to the determinant. So what will be the next step after this? You are going to get this one. I can show you that this is nothing but the determinant A, and this will be 0, and this is also equal to 0, and this is 0. And what is this? This is second row element with their respective cofactors. It's determinant A, 0, this is 0, 0, and this is the third, this 3 by 3 element. The third row with the third row cofactors is obviously determinant A. So finally, after multiplication of the original matrix with the adjoint matrix, you are getting this. Okay. Now this is a matrix. So which element is common in the matrix? Here we have seen that here determinant A is common. So we'll take determinant A common from that matrix. If we take determinant A is common from that matrix, what is left out? Because determinant here 1, 2, 3, 4, 6 elements are there, and in each row there is a determinant A. So therefore from this matrix you can take determinant A out. So here 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? So this is an identity matrix. Determinant A is equal to Y. So what was the theorem today? If A be any given square matrix of order n, then A into adjoint of A should be equal to determinant A into I. So which is the verifications, determinant A into I. Similarly, this other second part also is equally easy. You can take adjoint of A into A, and if you multiply, and obviously you can verify that this term is also equal to determinant A into I. This is identity matrix I. Okay. Let's move to another concept. There is another very important theorem. What is that? A square matrix A is invertible if and only if A is non-singular matrix. Now before I start this particular theorem, let me explain you that if we'll just revise one, two concept, then we'll start a proof of the theorem. First one is that invertible matrix. If A is invertible, then there exists another matrix B. This is the definition. I'm just repeating the definitions. If A is an invertible matrix, then there exists another matrix B, so that AB is equal to BA is equal to I. So what is B called here? B is the inverse of A. That means we write A inverse is equal to B. We have learned this concept in our previous class. Next, let us learn another concept. What is a singular matrix? Okay. A is said to be a singular matrix a square matrix A is said to be singular in case determinant A is equal to 0. Okay? Determinant A is equal to 0, then it is called a singular matrix. And what is non-singular matrix? A square matrix A is said to be non-singular matrix in case determinant A not is equal to 0. So these are the previous concepts needed to understand this theorem. So we are going to explain this. So our square matrix A is invertible. Most important is this. If and only if. So let us first assume that A is invertible. Let A is invertible. A is invertible matrix. Therefore, we can definitely write AB, BA equal to I, right? Already I have just explained you. If let A be an invertible matrix, then AB is equal to BA equal to I. So as the next steps, we'll take a determinant. Determinant AB, and we'll use this I, right? So now determinant AB. Okay, obviously we are going to use the property. Here determinant AB, here A is an invertible matrix and B is also another matrix of the same order. So here the order of both A, B are same. Okay, now we need one more step to understand that determinant AB, you can write here determinant AB is always is equal to determinant A and determinant B. Remember this, determinant A, determinant B, and determinant I. What is I? I is an identity matrix. And determinant I, that means determinant of an identity matrix is always 1. So it's 1. So observe this steps carefully. Determinant A multiplied by determinant B equal to 1. Okay. Therefore, this implies determinant A cannot be equal to 0. So it cannot be equal to 0. If both are non-zero number, then if they're non-zero, because these are the two determinants, they have got certain values. So if you multiply non-zero number, then only it's possible to get 1. So determinant A is not equal to 0. Therefore, A is non-singular. The halfway, the proof is done. We have to prove the converse part of this theorem. I repeat this. We are assuming A is invertible matrix, and from the definition of invertible matrices, AB, BA equal to I. So to prove these steps, we are using only AB and I. So AB equal to I, so we are taking determinant. Determinant AB equal to determinant A into determinant B, and determinant, this is an identity matrix of the same order. So it's 1, and determinant A into determinant B equal to 1. So naturally determinant A is non-zero. So determinant, if the determinant A is non-zero, so A is non-singular matrix. Next, the converse part. What is the converse part? Now in this case, first initially we'll assume that A is non-singular. First we'll assume A is non-singular. Let A is non-singular. A is non-singular matrix. A is non-singular matrix. A is non-singular matrix. Therefore, determinant A not equal to 0. We're assuming this is a converse part. We know we'll be using our important theorem. The previous theorem, A adjoints of A equal to adjoints A equal to determinant A into I. Just now you have done this theorem that A into adjoints of A equal to adjoints of A into A equal to determinant A into I. So next, what is the next step? The next step is, since we are assuming that determinant A is non-zero, so we can actually divide these steps by determinant A. So if we divide this steps by determinant A, what are you going to get? So we'll divide this one A, and we'll divide adjoints of A by determinant A. The adjoints of A by determinant A equal to this adjoints of A. That means each and every term will divide by determinant A, which is allowed because we are assuming that determinant A non-zero. So next one is adjoints of A by determinant A, and right hand side will be what? This determinant A, since you are dividing, it will be only I. So this implies A, and this is adjoints of A. What is adjoints of A? Adjoints of A is a matrix. A matrix adjoints of A you are dividing by determinant A. Determinant A is a number real or complex, it's a number. This adjoint of A you are dividing by a determinant. That means you are multiplying by a scalar. So obviously this will be a matrix. So you can just take this matrix as B. And adjoint of A by determinant A. This is symbol, nothing else. The adjoint of A by determinant A you are denoting by a symbol B. Because B is a matrix. Now here B A equal to I. So what I have said? That this is a matrix A, this is another matrix B equal to B A. That means A multiplied by B equal to B multiplied by A equal to I. Therefore, from these steps we can definitely say that A is invertible matrix. Therefore, we can write here, therefore A is invertible matrix. Is invertible matrix. So how did you start the second part, the converse part? Converse part we assume that let A be non-singular and we have proved that A is invertible matrix. That's why we have proved this theorem for the condition if and only if. Then finally we are getting, what will be B here? Here B will be the inverse of A. So here we are going to write our important steps. Here B is inverse of A. Now what is the value of B? B is inverse of A. That means A inverse. Now what is the value of B? The value of B is adjoint of A by determinant A, which is written in a very simple form, 1 by determinant A into adjoint of A. Okay, this is a very important formula for inverse. I'll just write this formula once more. So finally we got A inverse equal to 1 by determinant A into adjoint of A. This is a very important formula for calculation of inverse. Next, let us calculate the inverse of the matrix 2, 2 and 4, 3. How to calculate the inverse of a matrix. Now, solutions. We know A inverse equal to 1 by determinant A adjoint of A. Just now we have done with the help of the theorem. That if we consider this matrix as A, let us consider this matrix as A. Let A equal to 2, 2, 4, 3. Let us calculate this matrix as 2, 2, 4, 3. Now, according to the previous theorem, we got an important definition that A inverse is equal to 1 by determinant A adjoint of A. So first we will calculate determinant A. Determinant A is 2, 2, 4, 3. 2, 2, 4, 3. So if you calculate 2, 2, 4, 3, it will be 3 into 2, 6, 4 to the 8. 3 into 2, 6 and minus 4 into 2, 8 is equal to minus 2. Now we need to calculate adjoint of A. Adjoint of A of this 2 by 2 matrix. Adjoint of A. Adjoint of, how to calculate adjoint of A? In the beginning of this today's class I explained how to calculate the adjoint of A. We'll interchange then 3 and 2 element, this diagonal element. We'll interchange. Then 3 will bring in this position, 2 will bring in this position. So it will be obviously 3 and 2. Now non-diagonal elements will write as it is, but the sign to be changed. So this 2 will be minus 2 and this 4 has to be minus 4. So this is adjoint of A. So we got the determinant A and next you calculated the adjoint of A. Therefore, what is A inverse? 1 by determinant A multiplied by adjoint of A. So determinant A is minus 2 and adjoint of A is 3 minus 2 minus 4 2. 3 minus 2 minus 4 2. So this is the inverse of the given matrix. In case you want to find the inverse of 3 by 3 matrix, the method will be exactly same, only in case of 3 by 3 matrix. So if I can show you. So if you take a 3 by 3 matrix, let A11, A12, A13, A21, A22, A23, A31, A32, A33. So we are asked to calculate the inverse of this matrix. So 9 elements are there. You need to calculate the adjoints of this matrix. It means you need to calculate the cofactor of all 9 elements. So since there is no shortcut method to calculate the adjoints of this 3 by 3 matrix, each and every element cofactor you need to calculate separately. After calculation of the cofactors, say you are calculating the cofactors, you need to write adjoints. So you have to find adjoints of A. How will you find the adjoints of A? Of course, it will take some time to calculate the cofactor of the 9 element. Correctly, you calculate the 9 element cofactors. Then you write as this. The cofactor you write as this, like A11, A12, A12, A13, A21, A22, A23, A31, A32, A33. Write all the cofactor, 9 cofactor, then you take transpose. The moment you take transpose, you will get the adjoints of A. And initially, after getting the matrix, your step 1 has to be determinant A. You will calculate the determinant A. Then second step, you will calculate the cofactors. Then you will find the adjoints. And all these values you need to substitute in the formula 1 by determinant A and adjoints of A. And then you will get the inverse of 3 by 3 matrix. So today we are discussing some very important concept right from the minors. Okay, if we can have a quick look on what we have learned today are this. First, we have learned about the minors. We have learned about the cofactors. We have learned about the adjoints. We have learned about important theorems. We have learned about how to find inverse of a matrix. So these are the all very useful concepts that we have learned today. And thank you so much for watching my video. And next we'll be discussing another very important concept, that is solution of system of linear equations with the help of the matrix method. Till then, bye bye. Thank you.